Hello, physical science students, and welcome to this video about electricity and magnetism. We are going to look at the relationship between electricity and magnetism. We're going to talk about electromagnets, speakers, galvanometers, and simple electric motors. So we'll start with a little story here. In 1820, a Danish physics teacher by the name of Hans Christian Oersted found that there was a relationship between electricity and magnetism. He was doing a demonstration involving electric current, and he happened to notice a compass nearby that he had left near the electric circuit. And that compass needle, he noticed, was affected by the electric current. So he hypothesized that the electric current must produce a magnetic field around the wire. And also that the direction of that field would depend on the direction of the current. And indeed, he's right. We now know that an electric current creates a magnetic field. Any moving charges, like those in a current, produce magnetic fields. So this diagram here shows how we can have a current-carrying wire right here. And when that wire is carrying current, magnetic field lines form in circles around it. If that the direction of that current is reversed, these magnetic field lines will reverse as well. Their direction will be in the reverse. Also, the strength of the magnetic field can be increased if we increase the current in the wire, and the strength of the magnetic field is closer or is higher as we are closer to the wire. The strength of that magnetic field decreases as we get further away from the current-carrying wire. So these interactions between electric force and magnetic force made scientists realize that really electric force and magnetic force are part of the same force, and we call that single force the electromagnetic force. It's the attractive or repulsive force between electric charges and magnets. And electromagnetism is simply the interaction between electric charges and magnets. So what happens if we put current through a wire like this one that is in a loop, around a round loop like this? What happens to the magnetic field in this case? Well, when current is passing through a wire in a loop, the magnetic field inside the loop is stronger than the field around a straight wire. So this is kind of interesting if we want to begin to create stronger magnetic fields. In fact, if we were to make a coil like this one, we call that a solenoid, where we take a single wire and we wrap it into a cylindrical wire coil. It's a solenoid. When we create this shape and we pass current through this solenoid, the magnetic field inside the solenoid is stronger than the field inside a single loop. And the magnetic field around each loop in the solenoid adds together to form the field shown in the figure. So we call this an electromagnet. An electromagnet is simply a temporary magnet that is created when there is a current in a wire coil like this. Oftentimes, that wire coil, here as an example, will be wrapped around an iron core, and that's what's shown right here. The coil, the magnetic field of the coil temporarily magnetizes this iron core, and as a result, the electromagnet's field here can be extremely strong. It can be up to 1,000 times greater than the field of just the solenoid alone. So the properties of an electromagnet are just like any other magnets when there is current in this solenoid. When the current is flowing through here, this electromagnet has a north pole and the other end is a south pole. If it's placed in a magnetic field, it will align itself along the magnetic field lines. An electromagnet will also exert a magnetic force on other magnetic materials and other magnets. And it's very useful because the magnetic properties can be very controlled. For example, the strength of the magnetic field can be decreased by taking away turns on the wire, or the magnetic field could be increased by adding turns on the wire. And we can even turn off the electromagnet by shutting off the current to the wire. So we can make an electromagnet rotate by using other magnets. You know that if we put poles of the pole of the electromagnet next to a like pole of another magnet, these repel, whereas the south pole will be attracted to the north pole of this electromagnet. So when the electromagnet would be in this position, if it were connected with a rod here somehow that we're able to rotate, this electromagnet here will rotate so that its north pole will align itself next to this magnet's south pole, and the south pole of the electromagnet will align itself to the north pole of this magnet. So when an electromagnet rotates, electrical energy is converted into mechanical energy to do work, and this is very useful for us. Electromagnets do a lot of work in different devices, such as speakers, for one. Sound is produced by speakers because of the work that an electromagnet does inside that speaker. The electromagnet changes electrical energy into mechanical energy that vibrates the speaker cone, which ends up producing the sound that you hear. So how exactly does this happen? Well, the music itself, the musical information, produces changes in voltage, and those voltage changes vary the electric current in the electromagnet. So both the size and the direction of the electric current change depending on the information in the music file. This varying current, electric current, causes both the strength and the direction of the magnetic field in this electromagnet to change. That changing magnetic field causes the electromagnet to be either attracted or repelled to this surrounding permanent magnet. This permanent magnet is a fixed magnet, so the changing magnetic force in this electromagnet is forced to cause the speaker cone to move, and that causes the surrounding air to vibrate and create the sound waves that you hear and that you enjoy when you listen to your music. Another use for electromagnets are galvanometers. Those are simply devices that use electromagnets to measure electric current, and sounds like a big fancy thing, but you all have seen these. Your gas gauge is a galvanometer. In a galvanometer, the electromagnet is connected to a small spring. And when there's a current in the electromagnet, it rotates until the force by the spring is balanced by the magnetic forces on the electromagnet here. Changing the amount of current changes the strength of the force between the electromagnet and the permanent magnet. The amount that the needle rotates is related to the amount of current in the electromagnet. And if this is calibrated, it can be used to measure the current in a circuit. So in a car, there is a float in your fuel tank, which is attached to a sensor, and the sensor sends a current to the fuel gauge, and that fuel gauge is the galvanometer. And as the level of the float in the tank changes, the amount of current sent by the sensor changes, and the rotation of the needle changes. And the gauge is calibrated so that the current sent when the tank is full causes the needle to rotate all the way to the full mark. Another way we use electromagnets are in electric motors. Electric motors are simply devices that change electrical energy into mechanical energy, and you use these all the time. So here is a diagram of a simple electric motor. I would encourage you to watch this animation of it, or some animation of it, to get a better appreciation for what is actually going on here and the moving parts involved. It's also on the class website. The main parts of a simple electric motor include a wire coil, and this armature is actually the wire coil right here. It includes also a permanent magnet, and a source of electric current like the battery here. So there are also a few other components in the simple electric circuit. Brushes right here, and what we call a commutator segment right here. The commutator segment is connected to the wire coil, and the brushes here, they make contact with the commutator, which is a metal ring. The commutator and the brushes form a closed circuit between the battery and the coil right here. So when there is current running through the coil, the forces between the coil and the permanent magnets right here, the permanent magnet, cause this coil to rotate. And the inertia of the coil makes it continue rotating. The coil in this simple electric motor is going to continue to rotate unless the battery is removed or the energy source, whatever energy source is supplying the energy for this motor, when that source is depleted, then this coil will stop rotating. Quick review. We looked at the relationship between electricity and magnetism. We looked at what electromagnets are, how they work. We looked at some applications in speakers, galvanometers, and simple electric motors. Here are some different advanced ideas that might be exciting for you to look into and bring your work to class, and I look forward to seeing you.